think the video's up. And I have like 5 other things to do. Josh emailed me to do like 5 different. Yeah.
No audio, right?
No audio, no.
Okay.
Yeah. Sorry, have you been starting on time? Has John been starting on time? Okay, cool. So let's get started. So this lecture will be talking about advanced model learning, kind of going back to some of the stuff that we talked about a few weeks ago with model learning, but making it, scaling it up and making it more advanced. So last time, John talked about DQN with images and how we can really scale these reinforcement learning methods to work with raw inputs and raw high-dimensional inputs like images. And so this lecture, we're going to be talking about, can we use model-based methods rather than model-free methods with images and really scale those up. So just to recap, what is model-based reinforcement learning? This is something that Sergey covered a few weeks ago. And kind of the generic version is that first you have some base policy, for example, a random policy, that you use to collect a data set of transitions from the state X and the action that was taken U, along with the next state that was observed. And you collected this data set, and then in step 2, you learn a dynamics model that learns a function fxu that maps from the current state in action to the next state in action using your data set. And usually you use a mean squared error as written there to be able to predict that model. And f of xu is termed your model. That's like a model of your dynamics. It's able to predict what the next state is given your current state in action. Once you've learned this dynamics model, then you can backpropagate through this dynamics model in order to choose actions, for example, using ILQR or some other model-based RL method. And then lastly, you can execute those actions and add the resulting data to your data set such that when you experience new transitions, new parts of the state space that you haven't seen before, you can then update your model such that it is accurate in those places. And then repeat until you have a policy that can choose actions in parts of the state space that you want to be in. Okay, so this is model-based RL, and one thing that we didn't cover is what if these X's are observations? What if you don't have the state of the system? For example, in a POMDP. So in a POMDP, you only get to observe the observations, which are shown in O, and you don't get to observe the ground truth state of the system. In a sense, the state of the system, the true state of the system is a latent variable that maybe you want to infer from your observations, and you want to be able to act and apply these model-based RL methods to POMDPs when you only have access to the observations. Okay, so in this lecture, I'll be talking about 3 different approaches for doing this. The first is learning a model in the latent space, so basically inferring the latent state of the system and learning a model in that latent space. The second is learning a model directly on image space on the raw observations. And third, I'm going to talk about inverse models and how you can apply inverse models when you have observations. And one thing to note in this lecture is that really this is an active area of research, and there's really no single solution for how to solve this problem with high-dimensional observations. And so a lot of the things that I'm going to be talking about today are different papers and different approaches to solving this problem. And secondly, I'm going to be talking a lot about images and learning models on images, but observations, I just like to remind you, observations can be a lot more than images. They can be something high-dimensional like haptic feedback, language, really anything that just isn't uncovering the true state of the system. And the methods here are likely applicable to those sorts of observations as well. And the reason why there's such a big focus on images is that they're very cheap to obtain for robotic systems and other systems, and they're very expressive. So they include a lot of information about the world, but they're not directly accessible with some linear function, for example. OK, so first I'm going to be talking about models in latent space. And the key idea here is to learn an embedding that maps from your observation to your latent space. And then run reinforcement learning in your latent space. So let's take a look at this, this graphical model again. And what's going to happen here is that instead of learning a policy that maps directly from your observations to your actions, as in kind of the model-free way of doing things, we're instead going to learn this function g that tries to infer the latent state from the observation, and then learn a policy on top of that inferred latent state to take the actions, like in this graphical model. And once you have this latent embedding, you can actually apply really model-based or model-free methods to this. We'll see kind of the benefits of why you would apply a model-free method to using this method. And then a lot of the focus will be on model-based methods. And so the first question here is, what do we want G to be? So we don't necessarily know the ground truth latent state. And it could be a number of things. And you could have a number of representations for your latent space. And so it turns out actually that what we want G to be is going to depend on the problem and the way that we're actually going to be using G of O, as we'll see next. Any questions up until this point?
Is
yeah.
G deterministic or stochastic?
It can depend. If there is if there isn't any uncertainty in your observations, then you can make it deterministic. It's really a design choice. If there is uncertainty, for example, there's occlusions in the images, or there's some other sorts of uncertainty, then you can make it a stochastic function, where that's outputting a distribution over x. Yeah.
Okay, so is the G here really to serve for like dimensionality reduction, or is it actually because you can't observe the state? Like in the Atari game, isn't everything fully observed?
Yeah. So in Atari, things are fully observed because you're passing in a sequence of frames, like a history of 4 frames. So it can be for both. So it can be for dimensionality reduction, so as you saw in homework 2, like when you have a very low dimensional state of the system, you're going to learn very quickly. Whereas when you want to work with from images, it takes a lot longer. And if you have this low dimensional state, it can be a lot faster to learn. The other thing can be for partial observability. For example, if you only have 1 frame, you don't have the history of 4 frames, and you want to encode velocities in your state, you might have some recurrent embedding of your past sequence of observations that maps to your current estimate of x. Any other questions? OK. So the first method that I'll cover is a model-free based method that does this. And this is the paper. And in this paper, they're concerned with the problem of driving a slot car around a track. The car is on the track, and there's a slot on the track. And there's basically, as a 2-dimensional state of the system, the 1D position of the car along the track, as well as the velocity of the car along the track. And the action is just whether or not to accelerate or decelerate. And so the true latent state, the true state of the system is just 2-dimensional, as I said. And if we had that true low-dimensional state of the system, then we'd learn a lot quicker, as you saw in homework 2. And so the way this works is they first collected data with an exploration policy, and then learned a low-dimensional embedding of the image using that data. And I'll talk about how in a second. And then once they had that low-dimensional latent state, they ran Q-learning, just like you saw in the last lecture with function approximation, using that embedding as the state instead of the raw observations. And so how did they get that low-dimensional embedding? So they used what's called an autoencoder for dimensionality reduction. And I guess the first way to look at an autoencoder is that one way, if you wanted to do dimensionality reduction on an image, you might run PCA to get a linear embedding of your image. And that will try to encode the n principal components that you care about in a lower dimensional vector. In an autoencoder, this is just a nonlinear version of PCA where you're trying to recover a a lower dimensional version of the state where there's nonlinear transformations from your observation to your encoding. And so the input to the autoencoder is your observation in this case, and the output is a predicted reconstruction of your observation. And then the way that you train an autoencoder, so each parts of the autoencoder is a neural network, and you train the weights of your autoencoder to minimize the mean squared error between your true observation and your reconstructed observation, the output of the autoencoder. And note that if the autoencoder is a very expressive function, this can just be the identity. And we don't want to just learn the identity function. We want to learn something meaningful, learn something interesting. And so the middle of the autoencoder is usually what you care about. And the way that you actually try and learn something meaningful about the data is you put some sort of prior or some sort of bottleneck on that middle layer of the autoencoder. And so that could be a bottleneck. So in this case, the middle layer of the autoencoder is just 2 dimensions to represent the 2-dimensional late of the state. And when you have this bottleneck, it forces the information to be much lower dimensional than the full dimensions of the image. And then you can learn some sort of low-dimensional encoding of your image. But there's other ways that you could bottleneck the information and learn information. For example, say your bottleneck, say the middle layer of your autoencoder is denoted by Z. If you wanted to learn a sparse latent representation on Z, instead of doing a low-dimensional representation, you could put a L1 sparsity penalty on your latent encoding and add that to the objective, the objective on the reconstruction term in order to learn a sparse encoding. These are called sparse autoencoders, and they're very popular in the literature. Another thing that you could do is you could use what's called a variational autoencoder and put a prior term on that bottleneck layer that's encouraging it to have some sort of distribution. And usually, in that case, so say you want your latent state to be from it's a stochastic network, and you want your latent state to be a Gaussian distribution, a normal Gaussian distribution, then you would put a prior on your latent state. Say Q of Z is the output of your encoder of the network, and then P of Z is the prior distribution. Then you put a penalty of this form in order to encourage it to follow that distribution. And I'll talk a little bit more about that later. Question?
In terms of the terminology,
yeah.
When I usually hear embedding, I think of like going from a low-dimensional space to a higher dimensional space. Is it always the case that when you go into a lower dimensional space, or is it kind of interchangeable?
It depends on the problem. So in this case, here it's a low-dimensional state for the bottleneck. If it's a sparse function, then it could be higher dimensional. The dimensionality can vary, and it depends on what your inputs are too. If they're images, then typically it's lower dimensional. If it's something like a word embedding, where it's just a single word, then it's probably going to be higher dimensional. Yeah.
For the VAE, that should be Z given X, right? Or given
Yeah. This should be, yeah. So this is your encoder network, and this is your prior term on Z. Okay, so in this case, the function that maps from the observation to the bottleneck is G. And once you actually train this autoencoder, you throw away the network that maps from the bottleneck to the observation, and you just use that function G. And that's often what you do when you try and use autoencoders for unsupervised learning and feature learning tasks. Okay, so here's the full diagram of the system where they take the autoencoder, take that G, kind of throw away the latter parts of the network of the autoencoder, and then use that G function with Q-learning, run Q-learning just on G of O. So you take all of the O's in your data set, replace them with G of O, which is this nice 2D low-dimensional state of the system, and then run Q-learning with function approximation on G of O in order to learn how to perform the task. And indeed, in their paper, they show results where it's able to learn how to accelerate and decelerate at the appropriate times. Yeah.
So is the autoencoder only on single
Yeah, so the question was, is the autoencoder only on single frames? And in this paper, yes. So
There's only one embedding that's fed into the policy.
yes.
So how would you calculate something like velocity?
It learns what?
I don't know how.
Yeah.
It's all mysterious.
Yeah, I mean, in general, if you wanted to track something like velocity, you would use a recurrent network that is passed in the past sequence of observations to encode the prediction of the current x. In this, I'm not sure in this method.
If I had to guess, I'd say they must have fed in two, but I don't remember two images, but I don't remember them saying this in the paper.
Yeah, and the diagram certainly doesn't suggest that they pass in two images. Okay, so kind of the key takeaway here is that the embedding is low dimensional and summarizes the image. And because it's low dimensional, that makes the model-free method much faster. And so some of the pros of this paper are that it can learn the visual skill very, very efficiently using this low dimensional embedding. The cons are that the autoencoder might not necessarily recover the right representation, and it's not necessarily suitable for model-based methods, as I'll talk about next. And so the next paper that I'm going to talk about is a method that takes that learns this low dimensional embedding, then actually applies a model-based method for learning. And so this one starts off very similarly to the previous one, where we collect data with our exploratory policy, and then learn in this case, smooth and structured embedding of the image using the data that was collected. And I'll talk about how that is done next. Then learn a local linear model with that embedding, like Sergey talked about a few weeks ago, and then run iterative LQG on the learned embedding to reach an image of the goal and the goal gripper pose. And I'll talk a little bit more about why we represent the goal in that way in a minute. Okay, so first, how do we learn an embedding? How do we learn this smooth structured embedding? And so kind of the intuition here is that this paper was trying to learn robotic manipulation skills on a robot for manipulating objects. And generally, if you're manipulating objects, the part of the state that you're really going to care about, especially, so you know your joint angles, you know the gripper of the arm. You don't necessarily want to learn some embedding of the arm, since you can probably already observe that from the sensors on your robot. But what you really care about is where the objects are, because those are things that you cannot directly observe from measures of sensors on the robot. And so that's what we're going to try and learn in this embedding. And so the way that this embedding works is that it's an autoencoder, so it maps from the image that the robot sees, in this case a color image, and it tries to reconstruct a downsampled version of the original image. And it's downsampled because to reconstruct the full version of the image is quite high dimensional, and it's a little bit easier to reconstruct a smaller version. And the bottleneck in this case is much more high dimensional than the previous case. So before the bottleneck was two-dimensional. In this case, it's okay to have a higher dimensional system because we'll be using a model-based method. But the bottleneck here is encoding some structure in the image, which is it's going to try and pull out features, 2D feature points in the image, basically 2D coordinates of objects in the image. And the way that it does this is it takes a convolutional neural network that outputs some high-dimensional feature map after 3 convolution layers. And then it takes a softmax over the pixels in that feature map. And then for each and this softmax is over each feature map. So instead of actually being over the channels, which you would normally see in a neural network, the softmax is spatial. So it's over the extent of an image such that it kind of picks out the place of the highest activation in that image, in that feature map. And then once we take that softmax, we have a distribution over positions in the image. And we can take an expectation to get effectively the argmax of that feature map, basically the position in that image where the feature is most activated. And so mathematically how this works is that the softmax, say the last feature map is A for activations, and it maps over, it has indexes C, I, and J, C for channels, I for the X coordinate, and J for the Y coordinate. And then the softmax works by exponentiating. So the output of the softmax for coordinate Cij is going to be the exponential of a Cij divided by, we're going to sum over I and sum over j of, and I'll put primes on there to disambiguate, over the exponential of a c I prime j prime. So this is the softmax. And once we have the softmax, and then usually softmax has a temperature alpha, which will control how sharp, how peaked that distribution is. And then once you have the softmax, then the feature corresponding to channel C is going to be an xy coordinate. It's going to be an expectation over I of S Cij, and then an expectation over the j coordinate of S Cij. And so this will give you an xy coordinate of the feature of where basically the feature, where there is maximal activation in the feature map A. Okay, so that's how this works. And as a result, so here are examples of some of the features that we get. So in this image, this shows the initial image, and the red to green dots show a trajectory of that feature point over the next 100 frames in this case. So you can see that it's able to track where the gripper goes, as well as where the white bag goes. So in this case, unlike the previous example where the embedding was low dimensional, in this case the embedding is smooth and structured, which is going to be beneficial in model-based learning, so that we can actually learn a model on top of this low dimensional embedding. Any questions on how that works?
I have a question.
Yeah.
So for that expectation over there, how does it learn the gripper and the object both at the same time? I thought you only had.
Yeah. So this is a coordinate for the channel C, right. And then you have one of these for each of the channels in your features. Yeah. And this is just showing 2 of them. You might, in this case, we have 16 of them total. Okay, and so now we have our low-dimensional embedding of the image, and we need, because we aren't using the low-dimensional state of the system, we need some sort of reward or some sort of objective on our embedding in order to apply a model-based RL method, because we need some sort of way to know, given our current state or given our current embedding, what is the reward or what is the cost of that state? What is the cost of, we need some sort of mapping that tells us, given an image, what is the cost of that image? What is the cost of that embedding? And so what we're going to do is we're going to provide an image of the goal, as well as the goal gripper pose in this method. And for example, say that the robot wants to push this Lego block to the left. This would be an example of an image of the goal. And for example, this might be the initial state of where the robot wants to, of the scenario where the robot wants to push the Lego block to the left. Okay. And so here's the method learning. So it's initialized with a controller that generally knows how to move its arm to the left, but doesn't know how to get the Lego block to the right place. And as you can see, through learning over time, it learns how to actually make contact with the block and move it into the position that such that it matches the features of the goal image. Okay, and so here's the final policy that was learned. This is a bit of a toy task. It was also run on a much harder task where it's trying to use a spatula to lift up a bag of rice and insert it into the bowl, and it's able to, and this task is quite challenging because it has to fairly aggressively move the spatula underneath the object in order to lift it into the bowl. And it's able to succeed using this method. And lastly, one of the benefits of using these feature points is actually they're very interpretable. You can just plot them on the image. So if you take your feature points here, for each channel and for each image, for each frame in the video, we can plot them. So the X's are the goal, the feature points of the goal, and the circles are the feature points of the current frame. And so you can see how in the final policy it's able to match the features of the current frame up to the features in the goal frame.
Question.
Yeah.
Did you use 2 steps for the rice bag?
Yeah. Yeah. So actually, in the case of the bag of rice and inserting it into the lifting it into the bowl, we actually used 2 images of the goal because the model-based method couldn't handle. Well, so it's because it needed less of a sparse word, more of a word shaping. It needed kind of one kind of intermediate goal image and then a second goal image to actually get it into the bowl. Okay, so some pros. First, it's able to learn a complex visual skill very efficiently, and the structured representation enables effective learning. The cons are that the autoencoder, again, might not recover the right representation. So the reconstruction cost of the autoencoder, that's goal is just to reconstruct the image. And that objective isn't necessarily consistent with the objective of the task. And so there's still a chance that the feature points might not hook onto the objects that you really care about. Okay, and then the last paper that I'm going to talk about with latent space is a paper called Embed to Control, which is another model-based method, but they take a different approach to learning the embedding. And so the idea here is that, again, they're going to collect data and then learn an embedding of the image from that data. But when they learn the embedding of the image, they jointly learn the embedding as well as the dynamics model on that embedding. And then once they have the embedding in the dynamics model, they run ILQG to learn to reach the image of the goal. So again, like the previous method, they provide an image of the goal and then try to reach that using the model-based method, using ILQG in this case. Okay, so the way that this works and the way that they learn this embedding and the dynamics model jointly is, let's revisit our graphical model here. In this case, the O's are observed, and they're learning both the embedding G as well as the model P of xt plus 1 given xt and ut. And I'll go back to the board. So the way they do this is they consider a data set, again, of triplets of OT, UT, and OT plus 1. And then they'll call this their data set D. And they're going to train something that looks a lot like a variational autoencoder, except it's not just going to be on the observations O. It's also going to be on the triplet of an observation, an action, and an observation. And the structure of the autoencoder, the structure of the graphical model, is going to look just like the structure seen here, except that it's only going to be 2 steps. So they're essentially removing everything from here on in the autoencoder. It's just going to be a graphical model over O1, OT, XT, UT, and OT plus 1, and XT plus 1. And so the objective in this case, L of D, looks like a sum over the points in your data set, the triplets in your data set. They have, I guess this is, I shouldn't repeat symbols. This is a likelihood term on OT, UT, and OT plus 1. This is the likelihood of seeing that triplet. And then there is and this is going to be a variational lower bound on that likelihood. And then there's going to be a prior term on the KL between, I'm going to have this be Q of Z hat given OT and UT. So this is your next embedding given your current observation and your current action. And q phi of z given ot plus 1. And so this is the likelihood of seeing an embedding z given your next observation. And so this is, well, yeah, I'll go over that in a second. And so each part, there's 3 parts of the network. The first one maps from, is parameterized by phi, and it maps from the observation to your embedding. So this is just your encoder. This is what I denoted with G earlier. The second one is the model. So this is zt plus 1. And everything is, I'm using these to denote the stochasticity. So that each of these is going to be a stochastic network with probability distributions. So this is q phi of z hat given z and u. So this is the model in the latent space. And the last thing is the essentially what you could call the decoder. So this is the observations, which are another network P of O given Z. So this is what maps from your latent state back to your observation. So this is, if in the autoencoder way of looking at things, this is the network that maps from your latent state back to your observation, the reconstruction network. And so kind of what this looks like, the way that you practically do this is you have some OT, and then this maps to your latent state ZT. And so this is Q phi. And you also have something that maps from ZT and UT to ZT plus 1. And likewise, for your next state, you have an OT plus 1, and you have something, your same Q phi that maps from OT plus 1 to, oh, actually, I should say this is Z hat T plus 1. This is mapping to the true Z plus 1. And there's going to be a KL term between these two to encourage these two encodings to be the same, to be consistent, essentially. So the model that predicts Z should be consistent with the true embedding of Z. And then there's also a P theta that maps back from ZT to OT, and likewise from ZT plus 1 to OT plus 1. And that's what makes the latent embedding actually something that can reconstruct the image, and something that includes information about the image. So any questions on this? Yeah.
I mean, is there a way to just like see this as doing some sort of variational inference with some Q distribution?
Yes.
Or?
With yeah.
So it is, but I guess okay, for just some particular choice of Q distribution, where you just break the links between like the different time steps. Is that
Yeah.
what the factorization is doing?
Yeah.
Okay, got it. Okay.
Yes.
So quick question, what is the bonus loss?
Bound, sorry.
Oh, bound loss.
Yeah, so this is the variational lower bound on the triplet. So this is like a likelihood term. And I'll leave this up. We'll take a break in like 2 minutes, and I'll leave this up during the break, and you can look at it more. Okay, and so here's some of the results. So they tried this on 3 different synthetic domains. The first was balancing a pole. The second was balancing a pole. Well, the first one was swinging up the pole. The second one is balancing the pole. And so on the right, they show the prediction from their model, the one-step prediction, not the rollout of the prediction. And then the third task was to try and take this 2-link arm and reach a goal image of the arm. Okay. And then here's another example where the goal state is looks like that. So first it moves its arm in and then rotates its first joint. Okay. And then to conclude, I'd like to ask you guys something, which is why do you have to reconstruct the image? Why not just learn an embedding G that maps from your observations to Z and learn by basically, why not just learn a model that maps from O to ZT and ZT plus 1, OT plus 1. Why not just try and train a model such that you can predict its next latent state, rather than also having the arrow that reconstructs the image from Z. Yeah.
It's easier to visualize with the reconstructed image?
It is easier to visualize, and that is very nice. But there's something else that would go wrong. Yeah.
Might I just learn to map everything to 0 to minimize the error between the estimate?
Yeah, exactly. So if you're just trying to predict, if you're just trying to train an embedding such that you can predict the next embedding, there's a degenerate solution where what it can learn is just to always map from whatever observation was given to all zeros, and then, or to whatever, some constant. And then you're able to perfectly predict what the next embedding is. It just is always the same thing. And then you won't learn any embedding. And so that's why we need to have some sort of loss that is actually encouraging this embedding to be something meaningful rather than all zeros or some all constant. Okay, let's take a short 2-minute break, and then we'll continue.
Actually, just a question on the loss. So,
Yeah.
If you just do variational inference and you break all the links in time, is the lambda KL going to come out of that, or is that like an extra term? Because do you see what I'm saying?
So the variational inference is just on the OT, UT, OT plus 1.
Yeah.
So you're saying, are you breaking it across
Yeah.
the entire sequence or within that?
I guess I was just wondering, so say you're just do variational inference and I pick a specific Q, would the lambda KL term come out of that approximation? Because I don't think you would get like a lambda KL term from that. Or is that like an additional thing where you're saying, I want some extra regular?
The lambda KL comes out of the
Oh,
objective.
it does. So where does the lambda come from?
Oh, the lambda does not come out.
Yeah, I see.
The factor, yes,
I
yes.
see.
It should be a 1.
Okay,
It should be 1, but in
Got it.
practice, people usually,
change it.
yeah.
Because you just
Also, is the Q psi, is that just a mistake in their notation? Should it actually be a P psi?
So the paper used Q psi.
That seems like it's part of the model.
okay, yeah.
That would actually make sense, because then if you
Yeah.
multiply that by P theta, you actually get a full chunk of the model.
I see.
Yeah, that should be P.
And then you just multiply all the Q phi's together to get the variation.
Got it. Yeah. So the approximation is breaking the links across time. Is that roughly?
Yeah.
So I guess if you're
That's my guess
yeah,
at least.
yeah, because I guess you were training like a time series model though. Like if you did like an HMM and somebody broke the links across time, that would be like a terrible approximation of posterior, right? So,
Well, it depends on how much latent state there
Try
is.
not to write any more
So in
beyond
some
that.
sense,
Beyond here?
Yeah.
Okay.
After that, it's like the statement's going to
So in
Okay.
HTML, what you're trying to do is you carry information forward in time.
yeah.
I guess
Whereas
if
what
you
they're
really want to keep
what
it,
they're
you can
really
just
trying to do is try to
slide
bake this high-dimensional limit into
Slide the what?
the board. Like,
So
you want more
implicit in
room.
this is
Okay, yeah. And how far to the left can I go?
I see.
Pretty much where you wrote the
Okay.
O plus.
So basically, like here
breaking it up like this.
to here?
Yeah.
Okay.
This actually is like a perfect alignment.
There are
Okay.
since then there are other works on
I'll just like,
kind of Kalman filter style
Yeah.
neural net models.
Yeah, yeah.
One of
I
them
don't know if I'll actually.
Kalman filters.
Yeah.
One called structured variational
Yeah,
autofilters.
actually, I've read this.
So those propose more sophisticated models for doing this kind of model.
Got it. Yeah, that's actually what I was thinking, because there are ways, it's actually pretty easy if you, I mean, I don't, in this setting, I think it's probably a bit more complicated, but those models are pretty easy.
Yeah, well, and probably one of those models combined with this approach should probably do that. Because this was a little earlier and maybe didn't have all the rough edges smoothed out. You know?
Yeah, this is from 2015? Yeah, NIPS 2015.
Well, and I think the kind of tasks that you saw in the video sort of reflect that.
Yeah.
It's not super sophisticated.
I see. Okay.
But it's definitely something that's good to work on, I think.
It's a good idea for fun.
Maybe a good project.
And then we can know whether something like structured VNEs actually does better than
Yeah.
this.
Yeah.
It wouldn't help.
Cool, thanks.
Because
Okay.
So this is actually just very short. But
Do you think I can erase it? Okay. Okay, let's get started again. So what we just talked about was different ways that we can learn models in the latent space and learn in a latent space and then run learning in that latent space. And now we'll talk about models that operate directly in the image space rather than actually using the latent space for learning or for planning. And so the way that this problem is formulated is that we're given an observation and an action, and instead of trying to learn a model in the latent space, we're actually going to try and directly predict the next observation. And this is, in the case where when O is an image, this is just action condition video prediction or frame prediction, given the conditioned on the action as well as the previous image. And so the first paper that I'm going to talk about that does this was a paper at NIPS 2015. And they did it on Atari games. So this is going to be similar to the frames that you've seen in homework 3. So they have two different variants on the model. I'll talk about them in sequence. So the first model, what it does is it's a feed-forward encoding. So it takes a sequence of the past k frames and has a convolutional neural network that takes those frames, concatenates them together, puts them through the network. It actually does have some form of latent space, some sort of low-dimensional space, but it's not actually used for planning or for control. They concatenate the action to the lower dimensional state, and then decode that state back to the next frame. And so this is mapping from the past k frames and the current action to the next frame through a feed-forward neural network. The second version of their network is a recurrent encoding. So they take an image, they map it to, again, some lower dimensional state. It's not as low dimensional as the 2D case, but it's lower dimensional than the image. And then they actually have what's called an LSTM, or a long short-term memory, a type of recurrent network that takes in that has some sort of hidden state that is at the particular time step, and it also takes in the and that hidden state kind of is what maps the recurrence and keeps around information of the past images that were seen rather than just the image that was passed in. And then it takes that recurrence, it adds the action in to the network, and then decodes to the next frame. And so this is the recurrent version of the network. And so there's two key components beyond just this neural network architecture, which in this case is convolutional down to some encoding, and then up convolutional or deconvolutional back up to the full dimension of the image. And so the first key component is that they train it for multi-step prediction, which is instead of just trying to predict the next frame given the current frame in action, they try to predict a future sequence of observations, a future sequence of frames given the current frame and the future sequence of actions. And so what this looks like is that, say you have some neural network, which I'll just draw as a box, and you're passing in your observation OT, and ultimately, you're also going to be passing in your action UT, and then this black box is going to predict OT plus 1. And then At the next step, this is for the recurrent network. I'm going to have an arrow between these that's representing the hidden state. You're going to pass in ut plus 1 and ot plus 1 to get ot plus 2, and so on. And so this is mapping from your current observation and your current action to your next frame. And each block is doing that. But, and actually, I'm going to put hats on here to denote these are the predicted frames. And at each time step, when you are passing in a frame in order to predict your next frame, you have a choice on what you want to pass in here. What do you want this to be? It could be the ground truth OT plus 1, in which case you're just doing one frame prediction. You're just predicting, given my current OT and my current UT, what is my next OT plus 1. But you could also pass in your predicted, the OT plus 1, the frame that was predicted at the last time step. And if you pass in the frame that was predicted and you keep on doing that at each frame, then eventually you're going to be predicting for multiple steps. You're going to be predicting the frames for k time steps into the future, given just your first ground truth frame, as well as your entire sequence of ground truth actions. And so that's what is meant by a multi-step prediction. So in this paper, they predict up to 5 steps into the future. So they pass in the O hat t plus 1 for 5 steps, and they pass in each of the actions for 5 steps, and then roll that out to get the future frames. And so what this does is it produces a video, a video of the future frames. And the second thing that they do is that they, in this case, they use a form of curriculum learning in order to make the network, make it a little bit easier to learn how to predict video. And I guess one reason why curriculum learning is helpful here is that if you're predicting video, a very nice local optimum to get into, especially if a lot of the frame isn't moving, is to just predict the predict the same image over and over again. And generally with video prediction models, you need to somehow get over this local optimum and actually try and predict motion in the image. Question?
Can you briefly explain what you mean with curriculum learning?
Yes, I will. So yeah, the way that they do this, I'll also talk about scheduled sampling in a minute once I talk about how they do curriculum learning in this paper. So what they do in this paper for curriculum learning is they start by just doing one frame prediction, where they're always passing in, at every time step, they're passing in the true frame OT plus 1 at each time step. So they're just doing one frame prediction. They train the parameters of their network. And then once they're done with that stage of the curriculum, they start doing 3-frame prediction. So they initialize the parameters of their network to be the network that was trained with 1-frame prediction, and then start training it for 3-frame predictions where they pass in the ground truth OT every 3 frames. So then it's forced to start having to deal with the predictions that it's making with the network rather than dealing with the ground truth frames that are very clean. And then after they start doing, after they train the network for 3-step prediction, then they train the network for 5-step prediction. So they initialize with the network that was trained for 3-step prediction and then and only pass in the ground truth frame every 5 frames. So that's how the curriculum learning was done in this paper. There's also something known as scheduled sampling, which I believe was also a paper at NIPS 2015 by some folks at Google Brain. And the way that scheduled sampling works, scheduled sampling is a way for training these sorts of sequential generative models where you need to figure out whether you want to feed in the predictions or feed in the ground truth frames. And the way that scheduled sampling works is it models, it has some probability of passing in a ground truth frame versus passing in a predicted frame. And at the beginning of training, the probability of passing in a predicted frame is 0, and the probability of passing in a ground truth frame is 1. So it always passes in the ground truth frame, and it's doing 1-step prediction. Then over time, that probability is annealed such that it's always getting the predicted observations rather than the ground truth observations. So it's a form of the curriculum, it's more like a continuous form of the curriculum learning where it anneals the probability that it slowly increases the probability that the model is going to be seeing its own predictions rather than seeing the ground truth predictions. It's also worth noting that schedule sampling was originally designed for language modeling tasks, where it's trying to generate language, but it's also useful in these sorts of video generation tasks as well. The next paper that I'll talk about uses scheduled sampling instead of curriculum learning. Yeah.
How do you choose the 5 steps of 5 frames is the best prediction?
So you're saying how do they, why choose, like why not have larger than 5? Yeah, so in this case, they found that 5 worked well, and it was sufficient for making very good long-term predictions. They're actually going to test on much longer than 5 frames, as I'll show in a minute. It actually turns out that a paper after this did longer than 5 frames and seemed to get much better results by training for longer than 5 frames. I think in that paper they used 10 frames. And so it's a hyperparameter that you need to set. And the way that you generally set it is just by empirically looking at the results. Yeah.
And do they do this k-step prediction with the feed-forward encoding as well?
I believe so. It wasn't completely clear from reading the paper, but I believe they do.
And did do much worse than the current encoding? Or?
I'll show results on that in a second. OK. So now that we've talked about this, does it work? So here's an example of the predictions on the game Freeway. And on the left is the predictions rolled out from the model. And this is, in this case, I believe this is a 100-frame prediction. So this is not passing in the ground truth frame at every time step. This is just rolling out, given the initial frame and given all the future sequence of actions, what does the future video look like? And as you can see, the results are very impressive. So it's the predictions are very close to the ground truth, and it can successfully make up to 100-step predictions very accurately. OK, so what is the flip side of this? So actually, one thing you might notice with Freeway is that it's a very deterministic video. So the bottom lane is always a car that's always moving at some velocity, and so it's actually very easy to make these sorts of predictions. It's very repetitive, so this isn't too hard. Oops. And so here's an example on Sequest, which is a bit harder. And as you can see on the left side of the frame, on the left side of the video, it's actually failing to, when there are new fish that come out or divers that come out, it's actually failing to predict that those divers and those fish will appear. And so it's really failing to model a critical part of the game, which is that you want to know where the fish are and you want to know where the divers are so that you can know where to shoot and where not to shoot. But that said, this game is actually really hard because the fish and the divers kind of come out of nowhere. So it's hard to predict where they're going to come. There's actually a lot of uncertainty about where these things are going to appear and when they're going to appear. OK, this is getting back to the question earlier, which is that how does the feed forward and the recurrent network compare? So this is showing on the x-axis the number of frames predicted into the future, and on the y-axis the mean squared error. And in blue shows the feed forward network, and on red shows the recurrent network. So you can see on the first 4 games, the recurrent network performs much better than the feed forward network, getting much lower mean squared error. And on the last game, the feed-forward network does a bit better. So I guess the first thing to note here, these are evaluating using mean squared error on frames, which is a terrible metric as things go for predicting frames. And that's actually one of the things that makes video prediction very challenging, is we don't really have a good metric for what makes a frame accurate, what makes a prediction accurate. And the other thing is that I think that generally models that have some sort of recurrent state are able to perform much better, unless, especially for long-term predictions, unless the sorts of predictions, unless the sort of things that are happening in the video are very local and are very happen in very short time spans, like they do in Miss Pac-Man. Yeah.
What's the green NAF1 stand for?
I believe that's a baseline feed-forward network. OK, so can we actually use this for something? Can we use this for control? And so what they did is they used this model to try and inform exploration. and I'll say how they do this in a minute. But what they do is they try and use the model to basically try and explore the environment. So on the left, they show the informed exploration using the video prediction model, and on the right, they show random exploration. And as you can see, the model with informed exploration is able to visit and move, visit many more states and move and actually achieve a higher score in these cases. Okay, so how do they do this? So they take their video prediction model. Given the current state of the game, they store the most recent D frames. And then for every valid action from that state, they predict one frame into the future using their video prediction model. And then they take the action that corresponds to the future frame that is least like the previous D frames. So basically what they're saying is that they're going to try and go to the frame that they haven't seen before, something that looks different than the last D frames that they saw. And in practice, I believe they set D to be around 20 or between 20 and 200, depending on the game. And so what do they mean by like least like the previous D frames? What they use is they use the Gaussian kernel similarity metric on images using the equation here, and then they sum over the similarity metric over the D frames in order to get a score for each frame, and then take the minimum per action. And the one caveat here is that they're using this for exploration in order to explore more of the environment, but the prediction model was actually trained on data from a DQN network that saw a lot of the state, and so it was actually able to make reasonable predictions for different states. But if you're actually going to try this on a system that hasn't learned anything before and you want to be able to figure out how to explore new states, you're not going to have this data available to train your prediction model, and you'll need to train it more kind of from the ground up. So I think this is a kind of a, I don't know what the results would look like if they didn't do this, but in practice, if you wanted to do this for exploration, you would probably have to sequentially train your model as you get more and more experience to actually get some reasonable predictions about what the future states will look like. Okay, and the other thing to note is that this is a kind of very brief, well, first, you can use models for things other than planning. You can use it for exploration, and there'll be a lot more on exploration. Well, there'll be one lecture on exploration by John in a few weeks later in this course that will cover a lot more on techniques for exploring the environment and techniques for exploring the state space. Okay, so some of the pros and cons of this paper. With multi-frame prediction, they're able to get a lot of stability from their predictions. It's always also useful for control with the caveat that I mentioned before. And some of the cons are that synthetic images are a lot easier to generate. So as we'll see next, if you try and take this model on real images, it's really not going to work well. And it's also not immediately clear how you would try and plan with this. If you thought about it really hard, you probably could come up with something, but the way that generally to plan with it, you need some sort of reward function on the predicted images, which is not something that is immediately available. Okay, so what about real images? The next thing I'm going to talk about is two papers that does video prediction on images that were taken from a robot and actually used for planning. And so in this paper, we collected a lot of data on an array of 10 robots at Google and collected both a training set of videos that contain objects that were seen during training, and then we also collected a test set of novel objects that weren't seen in the training set. And the data is publicly available, and you can actually play around with it if you're interested in these sorts of video prediction models. And so then if you take the Atari model and run it on these video frames to try and predict frames into the future, given the first frame and the actions that the robot took, which in this case are the commanded pose of the arm, you get things like this. And this is evaluated on held out objects. So this is objects that weren't seen during training. And kind of the takeaway here is that the model really doesn't have the capacity to represent real images. So as we saw before in that network, it was going down to this somewhat low dimensional state. And with that low dimensional state, it's not able to model the complexities of real world images and model everything that can go on. And so in this paper, the model was formulated a bit differently. So they're doing action condition multi-frame video prediction, and the way it's done is via flow prediction. And so the kind of the key idea here is that instead of predicting a frame from the internal state of the model, it's going to predict how the previous frame can be transformed into the next frame. So the model is going to predict the parameters of an image transformation rather than predicting the raw pixels itself. And the insight here is that this transformation that is going to be predicted is a lot simpler and lower dimensional than predicting the image itself. And so kind of a toy example of how this is done, and one way that you can model this transformation is, so say the left image is your input image. Then the model predicts a normalized convolution kernel using a stacked recurrent network. And then it predicts multiple of these normalized convolution kernels. Those are applied to the image. So for example, the middle top image, the convolution kernel translates everything to the right, and the bottom translates things up and to the right. And then in addition to those convolution kernels, the model also predicts a mask over what parts of the image are going to correspond to that transformation. And so in this case, in this toy example, the model would be predicting that the top convolution kernel corresponds to the top part of the image, and the bottom kernel corresponds to the bottom right part of the image. And then the predicted mask and each of the transformed images are, the masks are applied to each of the images and then combined together to a single image, which, as you can see here, moves the triangle up and to the right and moves the circle to the right. And the intuition here is that generally objects are going to move in consistent ways, and the model is making a prediction for each of the different objects in the image, or each of the different segments in the image, of how they're going to move and how they're going to transform in the next frame. And then, as I talked about before, you can feed back the model's predictions for multi-frame prediction. And as before, it's trained with a mean squared error loss on frames. The model itself is a little bit more complicated than that. So it has, in addition to predicting the transformations, it feeds in the action, and there's also skip connections. But basically, a lot of the things that you would see in neural network type papers, and you can see details in the paper. And so here are some of the results. So on the left, I show the ground truth video, and on the right, I show the model's predictions rolled out. So this isn't one frame prediction. Again, it's doing multiple frames conditioned on the first frame and the future actions. And the first thing to note is they're a bit blurry. That's because of the mean squared error loss. As I mentioned before, it's not a great loss function, and the reason why it produces blur like this is that it's encoding uncertainty in the image using blur. Basically, by if it's not sure if the pixel is black or yellow, then it's going to take the mean of those two, and that's what the loss is encouraging it to do. But generally, even though they're blurry, it's able to fairly accurately represent motion of the arm and motion of the objects. Okay, so here are some more predictions. On the left is the predictions of the model that I just showed. And actually, there was some people at DeepMind who also tried a model on this data, and their predictions are shown on the right. In their model, they use what's called an autoregressive model that I won't go into in this lecture. But it's interesting to look at the predictions because on the right, you'll see the predictions are much sharper, so they don't have the blur because they're not using mean squared error loss. They're modeling the distribution over pixels. But instead of blur, they actually have a lot of warp in the objects as well as in the arm. And so, like, qualitatively, it's, I guess if you think about which, are these predictions good? Is one of them better than the other? Is one of them more accurate than the other? Or more useful than the other? It's really hard to evaluate, and that's really an open research question in the field of generative modeling, especially for video. And one of the things that you can use it for is for control, like I'll talk about next. So what are these predictions good for? So what you can use these predictions for is you can use it to predict what's going to happen in the future and imagine different futures based off of different actions that you took. And so in the third column, I show the videos that were predicted from the original actions in the database. But if you decrease the magnitude of the actions, basically tell the arm to move less and pass in those actions into the model, you get a different prediction. You get a different imagination of what's going to happen in the future. And so here you can see that the model predicts that the arm is going to move less if you pass in a smaller action magnitude. And if you decrease it even more, it predicts that the objects actually won't move. And likewise, if you go in the other direction, it predicts that the arm will move more. And so what this is doing is basically imagining different futures for what the robot might be doing in the future. OK, so how can you actually use this? So as we talked about before in model-based learning, we can plan with this model using model predictive control. So say this is your first image. And the way that we're going to do this, we're going to sample n potential action sequences, like maybe these 2 actions. And then predict the future for each action sequence. So maybe these are the 2 predictions for those 2 possible action sequences. And then we pick the future that we like the best and execute the corresponding action. And then we can repeat steps 1 through 3 to replan our actions for the future that we like best in real time. And so this is exactly model predictive control, except it's using images rather than using the ground truth state of the system. So one thing you might ask when you look at this is, how do you know which future is the best future? I just said that mean squared error really sucks. And so if we get in a goal image and try to compare them with mean squared error, it's not really going to give us a good answer. So which future is the best? So the way that this paper evaluates the future and which one we like the best is it specifies the goal by selecting where pixels should move. So it says that if we want to move this water bottle to the left, then you can just select the red pixel and say we want to move it to where the green outlined pixel is for both the triangles and the circles. If we want to rotate an object, we can also click on pixels and say where we want them to move it to. And then select the future with the maximal probability of the pixels moving to those positions. And because the model is actually modeling how pixels move, we can actually evaluate this probability and try and maximize it when we do planning. So how does this work? So the user can just click on a pixel and click on where they want to move it to. And then the robot plans to move the object according to that specified goal. So does this work when you try to evaluate on objects? So the method was evaluated on pushing short pushes of novel objects, so objects that weren't seen in the training set, for both translations and rotations. And the key thing to note here is that the only human involvement during training was just programming the initial actions for collecting the data set, as well as providing objects to play with and objects for the robots to push around. There wasn't any reward function that was specified other than just clicking on the pixels. So it was completely self-supervised. And with that, it's able to learn these very simple maneuvers of kind of trying to push objects towards the goal that was specified by the user, as well as rotate objects as was specified. So here we can see that if the object was, if it was instructed to rotate the object counterclockwise, it figures out how to push the object on the left side rather than on the right side. And likewise, if it's told to rotate it clockwise, then it eventually figures out that it needs to push on the right side of the object rather than on the left side of the object to rotate it. OK. So kind of the pros and cons of this method. The pros is that it's using real images, and there's very limited human involvement. So this can be scaled up to an array of 10 robots because you don't have to have a single human for every robot telling it what the reward function is, telling it how to do the task. And also, the approach should improve as video prediction methods improve. So this is video prediction is a very active area of research. I think there was like 3 or 4 papers at NIPS last year on video prediction, and several submissions at iClear this year. And so as video prediction methods improve, we should be able to improve methods that plan with video prediction methods. Yeah?
Do you view the model as kind of learning optical flow under the GUI?
So somewhat. So optical flow is given the current image and the next image, what is the flow between those two images. What this is doing is actually predicting future optical flow. So this is predicting, given my current image and not the next image, what is the optical flow that should produce the next image. Does that make sense? Okay, and so the cons of this approach is that despite the real images, there's limited background variability. So if you actually put a robot in the real world and it's looking out, it's going to see a lot more variability than the videos here. Yeah?
Is optical flow able to use as the images input to predict the steering angles for autonomous driving cars?
So you can't predict with optical flow, because optical flows assumes that you have the next image to predict the transformation. You can't directly use optical flow for predicting future video unless you just take the previous optical flow and run it forward.
I don't mean that predicting future frames, but just predicting control signals like steering angles for autonomous driving cars.
So you could use a method like this to plan steering angles, plan actions for a car. Does that answer your question? Okay. And some other cons are that the skills here are somewhat simple in comparison to what model-free methods can learn, and also some of the other model-based skills that I showed before. And the other thing is that it's very compute intensive at test time, and as a result, some of the skills learned were somewhat imprecise because it didn't have the compute to imagine all of the possible different futures for a different action. Okay, so lastly, I'm going to close with talking about inverse models. And so Igor talked a bit about inverse models and how you can plan and optimize behavior with inverse models. And here we're going to see if we can use them with images. And so I'd like to revisit the thought exercise that I brought up before, which is that do we need to reconstruct the image? Because reconstructing images are big things, and they're modeling everything in the image is actually quite hard. And there's parts of the image that really don't matter for the task. Like if you're trying to kick a soccer ball on a field, it really doesn't matter if there's a plane flying by or if there's some stranger walking by on the sidewalk. What you really care about is where the ball is and where it is in the image. And so if we can avoid trying to reconstruct the image and reconstruct everything that's going on, then maybe we can learn more effectively. And so the kind of key idea here is that instead of learning and embedding by predicting images, we're going to instead try and learn and embedding via an inverse model that is given the current observation and the next observation and tries to predict the action that was taken to get from that observation into the next observation. And so this is one form of supervision signal that we can use for learning. And this was done by a paper by Polkett, Ashvin, and others here at Berkeley on learning to poke. And so kind of the experimental setup is that they had this robot, and they wanted it to learn how to poke objects given an image and a goal image of where they wanted the objects to end up. And so the model was fed in an image, they collected a bunch of data of the robot poking objects and pushing them around. And then the model was fed in an image before the poke happened and an image after the poke happened. And they trained a Siamese neural network, which is essentially just a neural network with a neural network that takes in the image and outputs an embedding, and it shares the weights. But those two networks have the same weights, so they're trained together. And then the output of the embedding, the output of those neural networks are then combined together, concatenated together, and then passed in through a fully connected network to predict the action that was taken. In this case, the action is the poke. And so what they're predicting is like where they initialized the poke and what direction they moved for that poke. So it's a fairly low dimensional action. And what they did is so the embedding was at the last layer of this Siamese network that was mapping from an image, and they regularized this embedding with a forward model. So as I was mentioning before, if you have this embedding, at the end of a network, they had an additional loss. Instead of just trying to predict the action, they had an additional term in their objective that was saying that the embedding from one image should be predictable given the previous embedding and the poke. And then once they had this inverse model, they greedily planned with the inverse model and an image of the goal. So what they did is they took the current image and the goal image. It's possible that there isn't a single poke that can get you from this current image to the goal image, but what they did is they took each of the images, passed them through the action predictor, which predicts the poke that you can get from the current image to the goal image, and then they once they had the predicted action, they executed that action on the robot to get the next image. And then once they had the next image, they fed that image in again to then predict how to predict basically the next action to take to get from the next image that was observed to the goal image. Any questions? Okay, so here's a video of the data collection process. So they used a Baxter robot here at Berkeley. This is at 4x speed, so it moves a bit slowly. And in this case, the robot is poking around in a telebottle. And then they have the left arm of the robot kind of put the objects back into the workspace after it's been poking the object a few times. And they also collected data with multiple objects in the scene. And so here's the view from the table of it moving objects. And as you can see, some of the interactions are a bit unpredictable. If it actually runs into the object and then tries to move it, things that are a bit complicated can happen. The object can rotate, can move in ways that are fairly unpredictable. For example, here they show an example where it slips on the object, and instead of actually not moving, the object kind of slips and moves towards the robot. Okay, so some qualitative results of how this works. So the goal image is shown on the far right, and the initial image is shown on the far left. And each time step, you can see how the robot poked the object to get as close to the goal image as possible. And you can see on the second to last column the final image that was achieved by poking the object. And in the first two examples, it gets quite close to the goal image. Whereas in the second two examples, the actions it takes seem quite reasonable, but it doesn't quite get there. So for example, here it says to try and move the top of the hammer this way, which seems very reasonable to get here, but in fact that poke doesn't perform the right, doesn't result in the right transformation of the object. Okay, so to conclude, some pros and cons. One of the nice things about this, again, is it's very limited human involvement. It's completely self-supervised, and you don't have to reconstruct an image, which is really nice because there are things that you might not want to reconstruct. So the cons with this is that you can't plan with the inverse model. And so they really had to do this greedy planning scheme in order to try and reach the goal image. And the second thing is that the inverse model objective is trying to reconstruct the action, is trying to predict the action. And as a result, it really just cares about the action. And so it won't try and reconstruct the entire image and everything, but it will really just focus on what matters for the action, and it will ignore things that aren't relevant to the action, and it could potentially ignore things like the object or other task relevant things that aren't exactly correlated with the action. Okay, so I'd like to finish up with some kind of a comparison with model-based and model-free learning, because there's definitely some trade-offs between them, and there really isn't a single right answer for which one to use, and there's different scenarios for which model-based methods can be useful, and different scenarios where model-free methods can be useful. And so the pros of model-based methods is that it's really easy to collect data in a scalable way. If you have n different agents that you can collect data on, they can collect data in a self-supervised way in parallel without a lot of supervision. And once you learn a model, there's a possibility that you can transfer across tasks because the model is agnostic to the particular task that you're doing or the particular reward signal that you're getting. And in general, once you actually want to deploy these model-based methods, it typically requires a smaller quantity of supervised data, such as a reward function or such as other supervision in order to actually try and learn a policy or optimize for behavior using the model. The downside is that models don't optimize for task performance, unlike model-free methods. So once you have a model, you can optimize for task performance. But the objective for a model is to try and predict everything that's going to happen, which isn't always consistent with what you need for the task. Sometimes, and again, well, similar to the before, sometimes it's harder to learn a model than a policy because it's trying to predict everything, not just the action that it's going to take. So it can be a bit more complicated than the policy that you want to learn. And often, in order to learn complex skills, you need some sorts of assumptions. And this is something that Sergey mentioned in a lecture earlier, is that sometimes you need continuity, assuming that it's basically ability to linearize your model, as well as you might need reset. You might be able to reset the environment and reset the system in order to be able to form your model if you're trying to learn a local linear model. And then looking at model-free methods, one of the benefits is they make very little assumptions about beyond a reward function of what you need. You don't necessarily need continuity or resets of your system. It's very effective for learning complex policies, with the caveat that it requires a lot of experience, so it can be very slow to train. And it's not immediately transferable across tasks because you learn a single policy for that task, not a policy that can work for all tasks. And so to close, learning the right features is important. So learning the embedding that has the right information is very important for these methods. And if you're going to try and use a model-based method with images, then you're going to need to think about the reward or the objective when you're actually trying to use the model of observations. And next time, we'll talk about advanced imitation learning. See you on Wednesday.